In the previous video, we introduced hydrolysis reactions. And as a reminder, hydrolysis reactions can occur when you have an ester or an amide. And we're going to go ahead and look at this example with an ester. Okay, so the idea with hydrolysis is that water lines itself up with the ester bond and breaks the bond, right? So we mentioned that we know for sure that this is the bond that breaks between the carbonyl and the oxygen of the ester. And every single time you break a bond, you also have to create a bond. So if we've broken this CO bond, then we have to create a bond with this carbon and with this oxygen. So the carbon creates a bond with the oxygen of water, and the oxygen creates a bond with the hydrogen of water. Now each of these two atoms have created new bonds, so we now need to break this bond as well. So the product of this reaction ends up being a split ester. So we've split the ester, and on the carbonyl we end up with the OH from water, so we create a carboxylic acid, and the hydrogen from water ends up linked with the OH from our original ester. So this is our R prime. So we create a carboxylic acid and an alcohol. So in this video, we're going to quickly think about the energetics of this reaction. Because we said previously that this reaction happens a lot in our bodies, right? This is how we break fat down so that we can metabolize it and create energy from it. But for that to happen, we need this reaction to be energetically practical. So let's explore what has to happen for this reaction to occur. Using the scheme that we talked about before, where we're breaking a bunch of bonds and then reforming the correct bonds, right? Using bond enthalpies. What we would need to happen in this reaction is we would need to go from our original ester. This would need to split into the radical where we have an unpaired electron on carbon, and we would have this oxygen with an unpaired electron. And on water, we would need to break apart this OH bond, so we end up with a hydroxyl radical and a hydrogen atom. Right? And once we've done this, we can then reform pairs to make our covalent bonds. Right? So a couple of videos ago we described this process in terms of the bond enthalpies. So just to explore this a little bit further, this first reaction, breaking a CO bond, right, breaking a carbon-oxygen bond, requires 352 kilojoules per mole of energy. Breaking an OH bond, right, to create our oxygen and our hydrogen, requires 465 kilojoules per mole of energy. So overall, to reach the transition state, right, so to create these high energy intermediates, it would require 352 plus 465 kilojoules per mole of energy, which is 817 kilojoules per mole. This would be the activation energy. That's a lot of energy. It's so much energy, in fact, that it's simply not practical for these chemical reactions to happen quickly in the body. Okay, so what ends up happening is we don't actually follow this reaction pathway. Instead, these ester and amides, right, so this ester linkage here and an amide linkage, which was R with a carbonyl attached to a nitrogen, right, so these links are specialized such that they can go through a different reaction process, right? A different reaction pathway to facilitate a hydrolysis reaction. In the next video, we're going to explore that.